Beneath the quiet surface of Earth's oceans, far below the last reach of sunlight, there are places where the water becomes black, heavy, and almost still. The pressure there presses from every direction at once. The seafloor folds into trenches, vents breathe mineral heat into the dark, and pale animals move slowly through a world that should have been empty. It is one of the strangest frontiers on this planet, and it may also be one of the closest mirrors we have for distant worlds hidden beneath ice. Before this long journey begins, take a moment to settle into the room around you. If this kind of slow exploration through space, ocean, and the quiet edges of science feels like a place you would like to return to, consider subscribing, leaving a like, or sharing this with someone who also enjoys drifting through the mysteries of the universe at night. And wherever this finds you, whether it is late evening past midnight or somewhere in the soft hours before dawn, you are welcome to leave your country and local time in the comments. There is something quietly beautiful about imagining different people in different rooms, under different skies, listening to the same distant story. Let the lights grow dim if they are not already. Let the screen become less important than the sound. A fan can hum in the background. A blanket can settle into place. The body does not need to follow every detail. It only needs to float beside the story as it moves from the deep ocean to the frozen moons of the outer solar system, from tiny ancient cells to planets circling stars far beyond the reach of any human hand. The path begins here, not among the stars, but in water. Downward first, into the dark, where Earth keeps one of its oldest lessons. The ocean does not become strange all at once. It changes by degrees. Near the surface, light still breaks apart into blue and green, and the motion of waves still belongs to the world above. A body can imagine that place. It has wind, weather, the memory of shores and harbours. Then the descent continues, and the familiar things begin to fall away. Colour thins out. Warmth leaves. The water closes over itself in layers, each one heavier than the last, until sunlight is no longer a presence, but a fact remembered from somewhere far above. Down there, the planet keeps a darkness that feels almost cosmic. It is not the darkness of a room after a lamp has been switched off. It is older than that, larger than that. A darkness made by distance, depth, and pressure. The surface is still there, but it no longer matters in the same way. It might as well be another sky. Above, storms pass, ships move, clouds gather and scatter over the open sea. Below, the water remains black, cold, and slow, pressing inward from every side with a force no human body was made to endure. That pressure is one of the first bridges between the ocean and space, though it works in a reversed way. In orbit, the problem is almost nothing pressing at all. In the deepest trenches, the problem is too much. One place threatens to pull air and warmth away into vacuum. The other crushes with the weight of kilometers of water. They are opposite kinds of hostility. But to the fragile machinery of a living body, they are close relatives. Both places remove the ordinary rules of breathing, standing, touching, and moving. Both make the human form suddenly very small, a person floating above Earth inside a spacecraft and a pale fish drifting above the Hadal seafloor seem to belong to different stories. One is surrounded by vacuum and sunlight. The other moves through cold water under an ocean's entire weight. Yet both are held inside environments where up and down lose some of their old meaning. Gravity is still present in each case, but the body no longer meets it in the simple way it does on land. In water, buoyancy softens weight. In orbit, freefall hides it. Motion becomes slower, stranger, less certain. There is no flaw in space either, not in any human sense. There are only paths through gravity, curves around worlds, long arcs shaped by bodies too massive and too distant to touch. The ocean has its own version of that silence. It has canyons, plains, cliffs, vents and trenches, but most of them lie beyond ordinary sight. The sea floor spreads under the waves like a hidden continent. It is far away while being here. For a long time, the deep ocean was not a landscape. It was an absence on maps. Sailors crossed above it. Whales moved through its upper blue. Storms wrote temporary patterns on its surface. Below all that, the bottom remained mostly imagined, measured in scattered lines and guesses, a depth without a face. Space, by contrast, often seemed more open to vision. Telescopes could gather ancient light. Cameras could return the faces of the Moon, Mars, Jupiter, and Saturn. The sky was distant, but it gave back images. This is one reason the comparison between space and the deep sea lasts so long. It is not just poetry. It is a practical resemblance. Both frontiers punish easy access. Both require machines to go where flesh cannot remain. Both replace direct experience with signals. A spacecraft sends back images through radio waves crossing millions of kilometers. A deep-sea vehicle sends back sonar, video, pressure readings, and samples lifted through black water. In each case, the unknown is translated. The translation is never complete. A camera on the seafloor can show a white crab near a vent, a ribbon of mineral smoke, a slow animal passing through the beam of a lamp. It cannot fully bring back the cold, the pressure, or the sense of being sealed beneath the moving skin of the world. A telescope can show a moon of Jupiter, striped with cracks and covered in ice. It cannot place the hand against that surface, or let the ear hear how silent the sunlight is there. Science works through fragments first. This is where the deep ocean becomes more than a comparison. It becomes a rehearsal. On Earth, there are places where life survives without sunlight, without warmth from the sky, without any of the soft conditions that once seemed necessary. Around hydrothermal vents, water sinks into cracks in the crust, heats near the planet's interior, gathers minerals, and rises again in dark plumes. The chemistry there feeds entire communities. Tube worms stand like pale stalks. Crabs move in the mineral haze. Microbes use chemical energy in place of sunlight. That one fact changes the way distant worlds are imagined. A moon wrapped in ice no longer has to be dismissed because its surface is frozen and far from the sunday. A sea hidden under a shell of ice no longer has to be empty, simply because no daylight enters it. The deep ocean has already shown that life can gather around energy, not just light. It can use warmth rising from rock, minerals dissolved in water, and gradients invisible to the eye. The same thought moves outward, past Earth, toward the outer solar system. Europa circles Jupiter under a bright white skin marked by long fractures. Enceladus turns around Saturn and releases fine sprays of ice from its southern pole. Ganymede and Callisto carry their own buried possibilities beneath ancient surfaces. None of them look welcoming. They do not have forests, shores, clouds, or open blue seas. From the outside, they are cold worlds, pale and remote. Yet the lesson from Earth's depths follows them like a small lamp. The surface is not always the whole story. In that sense, the search for life beyond Earth does not begin only with rockets. It begins with descent. It begins with learning how a machine survives pressure, how a signal travels through water, how darkness changes the meaning of sight. It begins with the patience required to study a place that resists being known. The deep ocean teaches slowly. It does not offer answers as a bright discovery waiting in open air. It gives them in narrow beams of light, in samples, in movements seen for a moment, and then lost again in black water. The stars have their own black water. Between planets, between moons, between one small world and the next, there is a depth, no diver will ever cross by swimming. Still, the resemblance remains. One depth lies below the waves, the other begins above the atmosphere. Both ask for patience. Both ask for instruments. Both hold out the same quiet possibility that life, if it exists elsewhere, may first be found not in a bright landscape, but in darkness, water, and pressure. Long before any robot could be asked to cross the ice of a distant moon, there was another question, closer and quieter. How does a human being learn to work inside a place that does not welcome the human body? Space answers that question with vacuum, radiation, distance, and the slow confinement of metal rooms. The ocean answers it with pressure, salt, darkness, and walls of water. For NASA, the two answers began to touch. The agency was born for the sky. Its early purpose was to understand the atmosphere above Earth and the region beyond it, where satellites, spacecraft, and eventually people would travel. Yet the planet below was never separate from that work. Earth is the first world any space agency studies. Its clouds, storms, oceans, ice sheets, and shifting heat all belong to the same physical story as planets elsewhere. From orbit, the ocean becomes a single moving skin, blue and silver, wrapped around a rocky sphere. In the late 1970s, NASA began watching the sea with instruments made for space. CSAT, a dedicated oceanographic satellite, looked down at winds, waves, surface temperatures, and the shape of the sea itself. It did not descend. It did not feel pressure. It passed above the world and read the ocean from reflected signals, learning how water moves across a planet. This was not deep exploration in the old sense. It was remote sensing, patient and wide, the same habit of looking from afar that would later shape the study of other planets and moons. A satellite can see patterns no ship can see. It can follow the curve of a current across an ocean basin, watch storms gather heat, and measure the roughness of waves under clouds. The deep seafloor remained hidden, but the surface began to speak in a new way. The ocean was no longer only a place for sailors and divers. It became data, climate, motion, a system large enough to influence the whole breathing rhythm of Earth. The next step was smaller, lower, and more confined. Off the coast of Florida, below the shallow blue of the reef, Aquarius Reef Base rests on the seafloor. It is not large. It is a compact habitat, a cluster of rooms where people can live beneath the sea for days or weeks, surrounded by water on all sides. From the outside, it seems almost fragile, a small human pocket inside a much older environment. Inside, the space is tight. Beds, equipment, work areas, and entry points share the same limited volume. There is no long hallway to walk away into, no open field, no sudden escape into fresh air. The people living there become aquanauts, adjusting to a rhythm shaped by the sea outside the walls. Every task is ordinary and not ordinary at the same time. Eating, sleeping, checking instruments, preparing for work outside the habitat. The actions are simple. The setting changes everything. Aquarius was first designed for underwater science. Through saturation diving, the body reaches a state where the gases in the blood and tissues settle into balance with the surrounding pressure. That balance allows divers to remain at depth much longer than ordinary dives would permit. Instead of visiting the reef for a brief hour and then rising, researchers can stay near the seafloor and observe it through time. The habitat turns the ocean from a destination into a temporary home. That idea mattered to space agencies. A spacecraft is also a temporary home in a hostile place. The International Space Station circles Earth in open vacuum, but much of its daily life is not made of spectacle. It is made of maintenance, routine, science, limited room, shared air, and the constant knowledge that the outside environment is fatal. Aquarius offered a way to practice that rhythm without leaving Earth. It was a room beneath the sea that could teach something about rooms above the atmosphere. In 2001, NASA began the NEMO program, short for NASA Extreme Environment Mission Operations. The name suggests hardship, but the practice was often slow and careful. Astronauts traveled down to Aquarius and lived as aquanauts, learning how small crews behave when the door opens not into a hallway, but into an environment that demands preparation. They practiced procedures. They ran experiments. They moved through checklists. They learned the quiet pressure of working where a mistake might matter. Outside the habitat, the sea became a stand-in for space. Neutral buoyancy allowed the body to move in a way that partly resembled weightlessness. Tools did not behave exactly as they would in orbit, but they became slower, more deliberate, less obedient to ordinary land habits. A task that might be simple at a desk took on another shape underwater. Hands had to be patient. Movements had to be planned before they began. Communication mattered because the environment did not forgive confusion. This was not a perfect copy of space. No analog ever is. Water has drag, space has none. The seafloor has direction, texture, and nearby life. Orbit has the curve of Earth below and blackness above. Yet an analog does not need to be identical. It only needs to isolate part of the problem. Aquarius isolated confinement, delayed action, teamwork, suit work, and the mental softness that can come from days spent inside a small habitat with the same few people and the same unseen danger outside. The value of such a place lies partly in its humility. Before a moon landing, a Mars journey, or a long mission through the outer solar system, there are hours of practice in places that do not look heroic. A person checks a seal, a tool is misplaced, then found. A plan is changed because the environment changes it. The public sees the launch. The mission is shaped earlier. In quieter rooms, beneath the waves, astronauts could become familiar with a simple truth. The unknown is not only far away. It can surround a person on Earth, close enough to touch if the conditions are strange enough. The ocean outside Aquarius was not an alien sea, but it helped make alien seas imaginable. It showed how a small habitat can sit inside a world that does not care whether the people within it are comfortable. It showed how science continues when comfort is removed. From there, the connection widens. The ocean is not only a training ground for bodies, it is also a testing ground for machines, for sensors, for habits of patience, for ways of thinking about life where sunlight is weak or absent. A person in Aquarius looks out through a window into blue-green dimness. A future machine under Europa's ice may look out into black water that has never seen a sunrise. The two views are not the same. They are close enough to belong to one long preparation. The descent into the Hadal Zone is not only a journey downward. Near the coast, the ocean still has colours that belong to weather. Farther out, above the open trenches, the surface may look ordinary, with waves lifting beneath the same sky seen from land. Nothing on that surface announces the depth below. Then the seafloor drops. The Hadal Zone begins where the ocean has already passed beyond the abyssal plains. Below about 6,000 meters, in the long narrow trenches, carved where one piece of Earth's crust bends beneath another. These are steep, folded, V-shaped wounds in the planet's outer shell, places where geology moves with a patience too slow for the body to feel. Above them, the water column becomes a weight of almost unimaginable steadiness. Below them, mud, rock, and darkness gather in silence. At those depths, pressure is not an event. It is the condition of existence. It surrounds every surface, enters every weakness, tests every seam. Most machines built for shallower water would collapse before they reached the bottom. Most air-filled spaces would be crushed inward, not with a dramatic explosion, but with a sudden surrender to the weight above them. The human body, made for the thin comfort of the surface, has no place there without layers of engineering between flesh and water. The Mariana Trench is the name most often remembered. Its deepest known region lies nearly 11,000 meters beneath the surface. Deeper than Mount Everest is tall. If the mountain could be placed upside down into that trench, its summit would still rest below the waves. A whole world of height can disappear into depth. Yet the Hadal Zone is not one single place. Trenches curve through the Pacific and beyond, scattered like dark seams along the edges of tectonic plates. If their areas were gathered together, they would form a hidden continent of depth, not smooth or empty, but varied, broken, and difficult to reach. This continent has no sunlight. It has no seasons in the ordinary sense. It receives the faint rain of material falling from above, fragments of plankton, dust, shells, and the bodies of animals that have died in brighter water. That falling matter is called marine snow. It drifts downward through black water, carrying energy from the sunlit surface into places the sun never touches. By the time it reaches the trench floor, much of its richness has been used, broken apart, or consumed in the water above. What remains is sparse. Life in the deepest trenches often lives by waiting. But waiting does not mean emptiness. When a large carcass falls into the deep sea, the silence can change quickly. A dead fish, a squid, a whale, or any sudden concentration of food becomes a temporary gathering place. Scavengers arrive from the dark. Amphipods, pale and curved like small armored shadows, can appear in numbers that seem impossible for such a poor environment. They feed, and then the black water closes again. Near hydrothermal vents, the logic is different. Seawater slips down through cracks in the crust, heats near magma, reacts with minerals, and returns upward changed. It emerges as hot, dark fluid loaded with dissolved compounds. When that fluid meets the cold, deep ocean, minerals fall out of solution and build chimneys, dark spires on the seafloor that seem to smoke without fire. The smoke is not smoke, it is mineral-rich water. Still, in the beam of a submersible lamp, it looks almost like breath from the planet itself. Around these vents, ecosystems form in a way that once unsettled simple ideas about life. The animals there are not feeding on plants. There are no plants. No sunlight reaches them. Instead, microbes use chemical reactions to make energy, drawing on compounds such as hydrogen sulfide and methane. Larger animals depend on those microbes, either by eating them, farming them, or carrying them inside their own tissues. The chain begins not with light, but with rock, water, and heat. Tube worms can grow in clusters near vent flows, their red plumes extended into the water, while bacteria inside them perform the work that sunlight performs elsewhere. Mussels, crabs, shrimp, and fish gather in zones where the water is warm enough to bring energy, but not so hot that it destroys them. The margins matter. Life holds to the boundary. That boundary is one of the deepest lessons the ocean offers to astrobiology. Life does not simply seek comfort. It seeks usable gradients. A gradient is a difference that can be exploited. Hot beside cold, alkaline beside acidic, mineral, rich beside mineral, poor, electron, rich beside electron, hungry. The living cell is built around such differences. It keeps one side of a membrane unlike the other, and from that small imbalance, it does work. In the deep ocean, the planet provides those imbalances directly. Warm fluid meets cold water. Reduced chemicals meet oxidized seawater. Rock meets ocean. Darkness does not prevent this. Pressure does not prevent this. Distance from the sun does not prevent this. A world can be buried under kilometers of water and still hold the unevenness that living chemistry needs. This is why the Hadal Zone is more than an extreme place. It is a correction. For a long time, it was easy to imagine life as something tied to sunlight, air, moderate temperature, and the surface of a planet. The deep sea gently removes those assumptions. It does not say that life can survive anywhere. It says that the range is wider than expected. It says that the surface is not the only doorway. The animals of the Hadal zone are Earth life, shaped by Earth's long history, carrying the same deep ancestry as every bird, tree, and human lung. Yet their bodies show how far that ancestry can be stretched. Proteins must fold and function under pressure. Cell membranes must remain workable in cold. Enzymes must do their quiet chemistry where ordinary biological structures would fail. For the search beyond Earth, this matters because alien life, if it exists, may not announce itself through forests, animals, or anything large enough to be seen by a camera at first glance. It may begin as films of microbes on rock, chemical traces in water, cells gathered around a vent, or metabolism so slow that only patient instruments can detect it. The deep ocean teaches that a living world may not look alive from far away. A trench seen from above is only darkness underwater. A moon seen through a telescope is only a cold dot of light. Both hide their interiors. Both require descent, sampling, and caution. The Hadal Zone remains Earth's quiet reminder that the most important environments are not always the ones that shine. Some of them wait below, folded into pressure, receiving faint energy, holding life in places that once seemed empty. The first machines that enter the deep ocean do not move like conquerors. They move like careful guests in a place that can end them without effort. A small flaw in a seal, a weakness in a housing, a misjudged descent, and the water finds its way in. At great depth, pressure does not need much room to work. It only needs an opening. For a machine, the Hadal Zone is a test of patience before it is a test of discovery. Every instrument must survive the long fall through cold water. Every camera, battery, motor, cable, and sensor must be protected from pressure that would flatten ordinary equipment into useless shapes. The machine must carry its own light into a darkness that absorbs it almost immediately. It must make decisions slowly, because the environment gives little forgiveness and almost no natural guidance. Early deep-sea vehicles often depended on human control from above. A cable linked the vehicle to a ship, sending power downward and data upward. Through that tether, pilots could guide arms, lights, cameras, and sampling tools. The connection was comforting. It gave the machine a voice and a hand from the surface, but it also kept the vehicle tied to Earth's ordinary habits. A cable can snag, a signal can lag, a ship can drift. The worlds under ice will not allow that kind of guidance so easily. A future probe descending through the shell of Europa may carry a line behind it. But once a small underwater vehicle is released into the ocean below, every meter becomes harder to manage from far away. Ice lies above, water surrounds it. Radio waves cannot pass through the sea in a simple way. Commands may need to travel through a relay, a cable, and a long sequence of machines, each one sitting in a hostile place. The farther the swimmer travels, the more alone it becomes. This is why autonomy matters. An autonomous vehicle does not mean a machine with imagination. It means a machine able to read its surroundings, follow a plan, avoid some dangers, and choose among limited options without waiting for every instruction. In the deep ocean, that can be the difference between a useful mission and a silent loss. In an alien ocean, it may be the only way to explore at all. The loss of Nereus made this clear in a hard way. Nereus was built to reach the greatest depths of Earth's ocean, a hybrid vehicle able to operate with a thin fiber optic tether or in a more independent mode. It had already visited the deepest part of the Mariana Trench and returned with images and samples from a place few machines had ever reached. Then, during a dive in the Kermadec Trench in 2014, it did not return whole. Under the pressure of that descent, it imploded. Later, pieces of it were found at the surface. There is a quiet lesson in that failure. The ocean does not respect past success. A machine that survives one trench may still be broken by another. Engineering at the edge is not a finished achievement. It is a repeated negotiation with conditions that do not soften because a mission matters. Nereus became part of the long history of exploration in which loss is not the opposite of progress. It is one of the ways progress learns its limits. The machines that followed became smaller, lighter, and more cautious in their design. Orpheus, one of the vehicles developed with lessons from Nereus, was built for the deep sea with a different kind of future in mind. It is not only a tool for mapping trenches, it is also a thought experiment made of metal, glass, software, and pressure-resistant materials. What kind of swimmer could one day fit inside a mission to an icy moon? What kind of machine could be light enough to launch, strong enough to descend, and patient enough to search through black water without a human hand on every movement? The answer begins with terrain. The Hadal seafloor is not a smooth plain. It is broken by slopes, sediments, channels, and places where debris collects from the water above. An autonomous vehicle must learn to map while moving, building a picture of the ground from sonar, cameras, and navigation instruments. This is similar in spirit to the way a rover on Mars reads the land ahead, choosing paths across rock and dust. Light is another problem. In the deep sea, a lamp creates a small universe around the machine. Beyond that pale cone, the world returns to black. A camera can only see what the light reaches. And the light itself can change the behavior of animals that have never known day. On Europa, if an ocean exists, a machine's light might be the first brightness ever to move through that water. The search would not be only visual. A deep water vehicle carries instruments to sense temperature, salinity, pressure, chemistry, and sometimes the faint signatures of particles in the water. It can follow gradients, tracing where one condition changes into another. Around a vent, those gradients may point toward energy. Around a seep, they may point toward chemistry rising from below. In a buried ocean beyond Earth, gradients may be the first clues that the water is not merely present, but active. A machine does not need to know what life is to begin looking for where life could be. It can search for warmth in cold water, minerals in motion, particles suspended in currents, surfaces where chemistry gathers. It can notice that one region is unlike another. It can return to a place where the sensors changed. This is a modest kind of intelligence, but in deep exploration, modest intelligence can be enough to open a path. There is something moving about these machines because they are built for loneliness. They are made in bright rooms by many hands, checked, tested, named, sealed, and sent downward into places no hand can follow. Their cameras become a kind of shared eye. Their lights become the only local sunrise. When they work well, they allow human thought to enter a place where the human body cannot remain. That may be the shape of the first true exploration of an alien ocean. Not a diver, not a submarine with people inside, not a windowed vessel descending like a scene from old fiction. More likely, it will be a small autonomous swimmer, released from a cryobot after a long melt through ice, turning on its lamps in water that has been sealed away for millions or billions of years. It will not know wonder. It will only measure. The wonder will happen elsewhere, later, when faint data crosses ice, space, and time, and arrives as a signal on Earth. Beyond the orbit of Mars, past the asteroid belt, the solar system grows colder and less familiar. Sunlight still travels there, but it arrives weakened, spread thin across distance. The worlds that circle the giant planets do not receive the warmth that falls on Earth. Their surfaces are marked by ice, old impacts, and long silence. At first glance, they seem like places where water has become a memory. Then the measurements change the story. Europa, one of Jupiter's large moons, is covered by a bright shell of ice. From space, its surface looks smooth compared with many other moons, crossed by long reddish lines and fractures that wrap around the globe. It has few large craters, which means the surface is young in a geological sense. Something has renewed it. Something below may have shifted, cracked, and healed it again over time. Under that ice, evidence points toward a global ocean, not a small pocket of meltwater, not a hidden lake caught in a basin, a sea wrapped around the moon, buried beneath a frozen roof, possibly touching rock far below. Europa is smaller than Earth's moon, yet the amount of water it holds may exceed all the oceans on Earth. It is a quiet reversal. A world that looks frozen from the outside may be one of the wettest places in the solar system. The reason is not sunlight. Jupiter is too far from the sun for that kind of warmth to matter much at Europa's surface. The heat comes from motion, gravity, and strain. As Europa travels around Jupiter, it is pulled not only by the giant planet, but also by neighboring moons. These gravitational tugs flex the moon's interior. Rock and ice are squeezed and released in a slow rhythm, and that movement can produce heat. The process is called tidal heating because it is related to the same gravitational force that raises tides in Earth's oceans, only here it works through the body of a moon. This is one of the great changes in modern planetary science. A world no longer needs to sit close to a star to be considered interesting for life. It needs liquid water, useful chemistry, and some source of energy. The old picture of habitability was built around sunlight. The newer picture reaches into shadows. Europa is not alone. Enceladus, a much smaller moon of Saturn, also hides a sea beneath ice. Its surface is pale, reflective, and cold. But near its south pole, long cracks cut across the ice like dark seams. From those cracks, plumes of water vapor and icy grains escape into space. The moon is small enough that this seems almost impossible when first imagined, a tiny white world hanging near Saturn's rings, sending pieces of its ocean outward into darkness. Those plumes matter because they remove part of the barrier. Europa keeps its ocean mostly sealed. Enceladus lets some of its interior leak out. A spacecraft does not need to land, drill, or melt through ice to taste that ocean in a first, distant way. It can fly through the plume and measure the grains that strike its instruments. Salts, organic molecules, and signs of water rock chemistry can become clues lifted from a buried sea into open space. Ganymede carries another kind of scale. It is the largest moon in the solar system, larger than Mercury, and it has its own magnetic field. Beneath its icy crust, models suggest layers of liquid water and ice may be stacked deep inside, a hidden architecture where oceans could lie between frozen phases of water shaped by pressure. The idea is harder to picture than a single sea under a single shell. It is more like a layered interior, with water changing form as depth increases. Callisto, farther out from Jupiter, is darker and older looking, covered with craters that record long ages of impacts. It does not show the same youthful surface as Europa. It seems quieter, less altered, more ancient. Yet even there, measurements suggest the possible presence of a subsurface ocean. If that is true, then buried water may not be rare among the outer moons. It may be a common result of ice, rock, salts, radioactive heat, and gravitational history. These ocean worlds are not oceans in the human sense. There are no waves under an open sky. No moonlight crosses their surfaces from above and sinks into blue depths. Their seas, if present, are sealed away. The ceiling is ice. The darkness is complete. Pressure grows downward. The water may be salty, mineral-rich, and old beyond ordinary feeling. Some of it may have been isolated for timescales that make human history vanish. Still, the word ocean remains useful because it carries the central fact. Liquid water exists in large amounts. It can move. It can dissolve material. It can transport chemistry from one place to another. Water is not life, but it is a medium where life, as known on Earth, becomes possible. It lets molecules meet. It softens boundaries. It carries ions, heat, and waste. It gives chemistry room to wander. The deeper question is whether these oceans touch rock. A sea trapped between layers of ice may be chemically quieter. A sea resting on a rocky seafloor may be more active because water can react with minerals, gather energy, and perhaps form hydrothermal systems. On Earth, this contact between water and rock feeds deep ecosystems. On a distant moon, it could create chemical disequilibrium, the kind of imbalance that living systems might use. That word, imbalance, matters. A perfectly settled ocean is not enough. Life needs differences. It needs energy that can flow from one state to another. Around hydrothermal vents on Earth, hot, mineral-rich water meets cold seawater, and microbes use the chemical contrast. Under Europa's ice, under Enceladus's shell, something similar might exist if warm rock, liquid water, and the right compounds meet in the dark. No one knows whether they do in the necessary way. The honest answer is still unfinished. Instruments can infer oceans from magnetic fields, gravity, surface shapes, plume chemistry, and the behavior of ice. They can suggest salts, organics, and water-rock reactions. They cannot yet show a living cell moving through those buried seas. That gap is not a weakness in the story. It is the story. The outer solar system has become a place where uncertainty has shape. Europa, Enceladus, Ganymede, and Callisto are no longer just frozen moons circling giant planets. They are possible interiors, possible waters, possible chemistries. From the outside, they remain bright, cold, and distant. Inside, they may be moving slowly through darkness, carrying oceans that have never known wind, never reflected a cloud, and never opened to a shore. Enceladus is small enough to seem, at first, like a footnote beside Saturn. The planet fills the nearby sky with rings, shadow, and pale bands of storm. Around it move many moons, each carrying its own cold history. Enceladus is only one of them, a bright white body with a surface so reflective that it sends much of the weak sunlight back into space. From a distance, it looks quiet, almost polished, like a frozen stone left in orbit. The quiet is misleading. Near the South Pole, the ice is crossed by long fractures. They are often called tiger stripes, though the name is warmer than the place itself. Along those lines, the moon releases water vapor, icy grains, and fine material from below its crust. The plumes rise into space in pale curtains, not like smoke from fire, but like breath from an ocean that cannot otherwise be seen. Some of that material escapes far enough to help feed Saturn's faint E-ring. Some falls back, dusting the moon again with pieces of its own interior. This is what makes Enceladus different from many other ocean worlds. Europa hides its sea behind a shell that must be read from the outside. Enceladus offers samples. It does not open completely, and it does not make the search easy, but it sends tiny messengers upward from the dark. A spacecraft passing through those plumes can touch material that may have come from a buried ocean without landing, drilling, or melting through the ice. The moon leaks its secret into space, grain by grain. Cassini changed the meaning of that leak. During its years around Saturn, the spacecraft flew close to Enceladus and passed through the plume material. Its instruments detected water vapor, salts, organic molecules, and molecular hydrogen. Each clue was small by itself. Together, they began to describe an ocean that is not just water, but water in contact with rock, water carrying chemistry, water with possible sources of energy. Molecular hydrogen is especially gentle in appearance and serious in meaning. It can be produced when water reacts with certain kinds of rock, a process that also occurs around hydrothermal systems on Earth. In living cells on this planet, hydrogen can become part of metabolism, a way to move energy through chemistry. Its presence at Enceladus does not prove life. It does not even come close to that. It shows that one of the possible ingredients for a living chemistry may be present in the hidden sea. The same care applies to organic molecules. The word organic can sound as if biology has already entered the room, but in chemistry it simply points to compounds built around carbon. Carbon chemistry can arise without life. It can be shaped by heat, ice, radiation, water, and rock. Still, complex organics inside plume grains matter because they widen the set of possibilities. They say that the ocean below is not chemically blank. It has a language, even if the meaning is not yet known. In recent years, old Cassini data has continued to speak. Scientists found evidence for phosphorus in salt-rich ice grains from Enceladus, likely in the form of phosphates. Phosphorus is part of DNA, RNA, cell membranes, and the energy-carrying chemistry used by life on Earth. Before that detection, Enceladus already seemed to have water, carbon compounds, hydrogen, and signs of water-rock reactions. Phosphorus added another piece to the habitability picture, not life, a possibility made more complete. There is a difference between a habitable world and an inhabited one. That difference must remain clear. A kitchen can hold flour, water, salt, and heat without becoming bread by itself. A moon can hold water, carbon, hydrogen, salts, and phosphorus without producing a single cell. Habitability is a condition. Biology is an event, or perhaps a long chain of events, and no instrument has yet shown that such a chain has happened under the ice of Enceladus. That patience is part of the beauty of the search. The plume does not answer the largest question. It only makes the question sharper. If there is an ocean below the South Pole, and if that ocean touches rock, and if chemical energy flows there, then Enceladus becomes a natural laboratory in the outer solar system. It becomes a place where water, minerals, cold, pressure, and time may be working together in darkness. The scale is quiet, not grand. Enceladus is much smaller than Earth's moon. Its gravity is weak. A person standing there, inside some impossible suit, would feel very light beneath a black sky and the wide arc of Saturn. The surface would be hard ice, bright enough in sunlight to seem almost clean. But under that brightness, the moon may hold a sea that has been sealed away from the sun for ages. Down there, if heat rises from the rocky interior, it would not look like day. It would be warmth without sunrise. Even after Cassini ended, the plume remained a living target for instruments far from Saturn. JWST has observed water emission from Enceladus on a scale large enough to show that the moon is not only venting for a moment, then falling silent. Its activity appears steady enough to keep feeding water into the surrounding Saturn system over long stretches of time. That steadiness matters. It suggests that the hidden ocean is not a rare accident caught in one brief outburst, but an ongoing exchange between the interior and space. The plumes create a strange kind of mercy for exploration. A future mission may not need to break the moon open. It could fly through the spray, again and again, tasting the grains with far better instruments than Cassini carried. It could measure the sizes of particles, the mix of salts, the carbon compounds, the isotopes, the patterns that chemistry leaves behind. It could ask whether the ocean is merely active, or whether something in that activity has the uneven, selective character associated with biology. Even then, the answer may not be simple. A signal could be suggestive without being final. A molecule could have two origins. A pattern could be made by rock as well as by cells. The best science does not rush past that uncertainty. It sits with it, tests it, and returns with better questions. Enceladus keeps releasing its ocean into space. The plumes rise, spread, freeze, and fade into the Saturn system. They are small compared with the rings, small compared with the planet, small compared with the long dark beyond. Yet inside those grains may be one of the most direct messages from any hidden sea beyond Earth. Not a message written for anyone, a natural one. Salt, ice, carbon, hydrogen, phosphorus, and water, carried upward from a place no eye has seen. Europa's surface keeps its silence in the oldest way. It is not empty, and it is not smooth, but from far away it gives almost nothing away. The moon shines with a pale brightness beside Jupiter, wrapped in ice that reflects the sun with a cold, clean glare. Long reddish fractures cross the surface like lines drawn and redrawn through frozen skin. Craters are rare. The ice looks young, disturbed, repaired, and broken again. Something underneath has been moving. That movement is not visible as waves. No open sea lies under a sky there. Europa's ocean, if the evidence is being read correctly, is buried under an icy shell that may be many kilometers thick. The surface is the roof of the sea. Above it lies radiation from Jupiter's fierce magnetic environment, a black sky, and the distant Sunday. Below it may lie a global body of salty water, dark, pressurized, and old. Europa is one of the reasons the search for life in the solar system changed its shape. For a long time, Mars held the central place because it once had rivers, lakes, and perhaps a warmer surface. Europa offered something different. It did not show a lost ocean carved into dry ground. It seemed to hold an ocean still present, still sealed away, still possibly interacting with rock and chemistry beneath the ice. The evidence arrives indirectly, as it often does in planetary science. Spacecraft have measured Europa's surface, its magnetic response, its gravity, its color, its cracks, and the way it sits inside Jupiter's system. A salty ocean can conduct electricity, and when such a moon moves through Jupiter's magnetic field, it can create a response that instruments can detect. The ocean is not seen with the eye, it is inferred, like a shape behind a curtain. That hiddenness is part of Europa's power. Enceladus throws some of its ocean into space. Europa is more guarded. It holds the question under ice. To reach the water directly, a future mission would need to cross a frozen shell, survive radiation at the surface, melt or drill downward, keep itself clean enough not to carry Earth microbes into a possible habitat, and then release a swimmer into a sea no living eye has seen. Each step is difficult. Together, they form one of the most delicate problems in exploration. Europa Clipper is built for the first part of that patience. The spacecraft is not designed to land or melt through the ice. Its work is reconnaissance. After launch, it travels toward Jupiter, where it is planned to orbit the giant planet and make dozens of close flybys of Europa. That path keeps the spacecraft from spending all its time in the most damaging radiation while still allowing repeated looks at the moon from different angles and distances. On each pass, instruments can work together. Cameras can study the surface in detail. Spectrometers can read the materials exposed in the ice. Thermal instruments can look for places that hold heat differently from their surroundings. A magnetometer can help refine the picture of the ocean below. Ice-penetrating radar can send radio waves downward and listen for echoes from layers, fractures, and perhaps the deeper structure of the shell. Gravity measurements can add another clue to the interior. The purpose is not to photograph a fish under the ice. It is not to find a simple sign and declare the moon alive. The goal is quieter and more careful, to ask whether Europa has the conditions that could support life. Liquid water is one condition, chemistry is another, energy is another. Stability through time may matter too. A living system, even a microbial one, needs more than a place to sit. It needs a way to keep its chemistry from settling into stillness. The surface may preserve part of that story. Europa's ice is marked by ridges, bands, dark stains, and broken plates that seem to have shifted and refrozen. In some places, the terrain looks chaotic, as if blocks of crust were loosened and rearranged before freezing again. Such regions may record exchange between the surface and the interior. If material from below has ever risen upward, or if surface compounds have ever been carried downward, the ice could be a slow archive between two worlds, the irradiated surface and the hidden ocean. This exchange matters because Jupiter's radiation is both danger and tool. At the surface, energetic particles can split molecules apart and create oxidants, chemically reactive materials that might be useful if they reach the ocean below. Radiation makes the surface hostile to life, as known on Earth. But it may also help make ingredients that, once buried and mixed into the sea, could feed reactions in darkness. A threat at the surface might become part of an energy story below. That is the kind of reversal Europa invites. The same environment that makes the moon hard to explore may help make it chemically interesting. The ice protects the ocean from direct radiation, yet the surface radiation may prepare useful compounds. The distance from the sun makes the surface frozen, yet tidal flexing may keep the interior warm. The shell hides the ocean, yet cracks and disturbed regions may leave hints of what lies beneath. No single observation can carry the whole weight. A warm region could have several causes. A surface compound could be made above, not below. A radar echo could be difficult to interpret. A possible plume could appear uncertain, faint, or temporary. Europa asks science to work in layers, checking one clue against another until a picture becomes more stable. The future cryobot remains beyond Europa Clipper, more dream than mission plan, but the idea has a quiet inevitability. A probe would land on the ice, anchor itself, and begin to melt downward. It would carry heat, instruments, power, and perhaps a long communication line trailing behind it through the refrozen tunnel. Its descent would be slow. Around it, the ice would close, melt, and change. The machine would pass through layers that might contain salts, trapped gases, and histories of cracking. If it ever reached the ocean, the first moment would be almost impossible to imagine without making it too dramatic. There would be no human witness standing there. No sound would travel back in an ordinary way. A small vehicle might slip from the melted shaft into black water, turn on a light, and measure pressure, temperature, salinity, particles, and currents. It might follow chemical gradients. It might look for suspended material, seafloor signals, or warmth rising from below. That moment is still far away. For now, Europa remains a moon of hints. The ice reflects sunlight. The cracks hold their reddish stains. Jupiter fills the sky with gravity and radiation. Beneath all of it, a buried ocean may move slowly against rock, sealed from sunrise, carrying the possibility that life does not need an open sky to begin. Only water, energy, chemistry, and time. The search for life becomes stranger when no ocean can be entered, no ice can be crossed, and no sample can be lifted into a waiting instrument. Around other stars, planets are not places with nearby horizons. They are points of light, brief shadows, faint changes in a star's glow. They do not give up stones, water, or cells. They give light, and from light, science tries to read air. A planet crossing in front of its star blocks a tiny fraction of starlight. Most of that light is simply dimmed, but a very thin part passes through the planet's atmosphere first. Molecules in that atmosphere absorb certain wavelengths and allow others through. The result is a pattern, a kind of chemical fingerprint, written not in ink, but in missing colors. From that faint pattern, instruments may infer water vapor, carbon dioxide, methane, oxygen, or other gases. It is a delicate act. The signal from a small rocky planet is thin beyond ordinary imagination. It must be separated from the much brighter star, from the telescope's own noise, from the effects of clouds, haze, and the limits of the measurement. The planet itself may be hundreds of trillions of kilometers away. Nothing in the instrument touches it. The whole world arrives as a small change in light. This is why biosignatures are never simple. A biosignature is a sign that could point toward life, but the word could is doing much of the work. Oxygen in an atmosphere may suggest photosynthesis, because on Earth, much of the oxygen in the air is maintained by living organisms. Yet, oxygen can also be produced without life under certain conditions, when water vapor is split by ultraviolet light and hydrogen escapes into space. Methane may suggest biology in one setting, but geology can make methane too. A haze may be biological, photochemical, or both. The search is not for one magic gas. It is for context. On Earth today, oxygen and methane exist together in a way that requires continual replenishment because they react over time. Their coexistence can be interesting because it suggests an active planet, one where chemical disequilibrium is being maintained. Life is very good at maintaining disequilibrium. It keeps systems from settling. It pulls energy through membranes, builds molecules, breaks them, releases waste, and changes its surroundings. A planet with life may carry that restlessness in its air. Still, a restless atmosphere is not proof. Volcanoes can breathe gases. Stars can strip atmospheres. Oceans can absorb carbon dioxide. Rocks can react with water. Radiation can split molecules and remake them. Even a dead planet can have chemistry with motion in it. The difficulty is not only finding a signal, it is learning how not to mistake an active world for a living one. There are other kinds of biosignatures that move more slowly. A planet may change with seasons. On Earth, carbon dioxide rises and falls as plants grow, decay, and grow again. Vegetation changes the reflection of light from the surface. Snow, water, rock, soil, desert, ocean, and plant life each return starlight in their own way. If a distant observer had a powerful enough instrument, Earth would not be a single, unchanging blue dot. It would pulse gently through time. Temporal signatures, the signs that change with time, are especially subtle. A seasonal shift in gases could be biological, but it could also come from temperature, clouds, circulation, or chemical reactions driven by sunlight. A change in color could be vegetation, minerals, ice, dust, or ocean glint. The planet must be watched again and again, not as a snapshot, but as a breathing pattern. Surface signatures add another layer. Every material reflects light differently. Water absorbs and reflects in one set of wavelengths, ice in another, rock in another, living pigments in another. On Earth, plants show a strong change in reflectance at the edge of visible red and near-infrared light. This is sometimes called the vegetation red edge. and it comes from the way leaves use visible light for photosynthesis while reflecting much of the near-infrared. To a distant telescope, a whole forest might become a small step in a spectrum. But life does not have to be green. That assumption belongs to Earth now, not necessarily to every living world. The earliest biospheres here may have looked different. Some microbes use pigments that reflect purple tones, and some researchers have suggested that a much younger Earth could have carried a purple tint if such organisms were widespread. Whether or not that image describes the planet exactly, it opens the imagination in a useful way. A living world may not advertise itself in familiar colors. A surface biosignature could be red, purple, dark, pale, or something no human landscape has trained the eye to expect. It would depend on the star, the atmosphere, the chemistry of the surface, the available energy, and the organisms themselves, if organisms are present. Around a red dwarf, photosynthesis might adapt to a different balance of light. Under a hazy sky, life might use wavelengths that pass through the atmosphere most easily. The color of life, if life has a color at all, may be local. That is why the patient approach matters. A distant planet is not judged by one feature. Its star must be understood. Its orbit must be known. Its size and mass must be estimated. Its temperature must be considered with caution, because temperature on paper is not climate. Its atmosphere, if detectable, must be read as a whole. Water vapor beside carbon dioxide means one thing. Methane beside oxygen means another. A thick haze can hide a surface. Clouds can confuse a spectrum. A star's activity can mimic or erase atmospheric clues. False positives are not failures. They are part of the discipline. They force the search to become deeper and more honest. A signal that once looked like life may turn out to be geology. And that is still knowledge. A planet that seemed promising may become less promising when its star is better understood. Another, quieter world may become more interesting when several modest clues begin to align. The work is slow because the question deserves slowness. There is also the opposite problem, false negatives. A living planet might hide its life well. Earth itself would not always have been easy to recognize as alive. Before oxygen filled the atmosphere, a distant observer might have missed the biosphere entirely or misunderstood it. Microbial life can alter a planet without making a loud atmospheric signature. A buried ocean under ice may be alive without showing anything clear at the surface. The absence of an obvious sign is not the same as absence of life. This uncertainty gives astrobiology its quiet tension, but not a dramatic one. It is the tension of listening through a wall, of reading a letter with half the ink faded, of watching a candle from across a valley and trying to know what room it lights. The science is careful because the distance is so large and the desire is so strong. It would be easy to see life where there is only chemistry. It would also be easy to miss life because it does not resemble home. In the end, reading life without touching it means accepting that light is both messenger and veil. It carries evidence across space, but it also arrives thinned, altered, and incomplete. A planet may pass before its star for a few hours, and in that brief dimming, a telescope may gather the faintest outline of an atmosphere. Somewhere in those missing colors, there may one day be a pattern that does not stand alone, but gathers with others into something harder to dismiss. Not a shout from another world. More likely, a balance of gases that should not remain balanced, a surface color that changes with seasons, a chemical pattern that keeps returning after every doubt has been tested. Life, if it is found from afar, may first appear not as an image, but as a stubborn imbalance in the light. Long before Earth became the blue planet in the familiar photographs, it may have worn other colors. The oceans were still oceans, but the air above them was different. The continents were not arranged as they are now. The sun was younger, dimmer, and the living world, if seen from space, may not have announced itself with forests, grasslands, or the green of leaves. Those came much later. The earliest life did not begin with trees, it did not begin with flowers, animals, or anything that could cast a shadow large enough to notice from orbit. For most of Earth's history, life is microbial. It lives as cells, films, mats, colonies, and chemistry spread thin across water, rock, salt, and sediment. It changes the planet quietly before it ever becomes visible in the forms that feel familiar. This matters because a living planet does not have to resemble modern Earth. The blue oceans and white clouds are only part of the present story. The green land is younger still. If another world carries life, especially young life, microbial life, or life adapted to a different star, its surface may not look like the image held in human memory. It may not be green at all. One old possibility is purple. The idea comes from organisms that use a light-sensitive pigment related to retinal, a molecule also involved in vision in animals. Some microbes, especially certain archaea living in salty environments, use proteins such as bacteria rhodopsin to capture light and help move protons across a membrane. That movement creates an energy difference, and the cell can use that difference to do work. It is a simpler kind of light use than the photosynthesis found in plants, and it does not require the same complex machinery. Bacteria rhodopsin absorbs greenish light and reflects more red and blue, which can make the cells appear purple. In shallow, salty waters where such organisms grow thickly, the color can become visible even to an ordinary eye. On the scale of a planet, if similar pigments were widespread enough, they could change the way that world reflects starlight. A distant telescope would not see individual cells. It would see a spectral trace, a surface color, a hint. The purple Earth hypothesis does not say with certainty that the young planet once glowed purple from space. It is more careful than that. It suggests that before oxygen-producing photosynthesis rose to its later power, other ways of using sunlight may have been widespread. Retinal-based systems may be ancient because they are chemically simpler than chlorophyll-based photosynthesis. A world filled with such microbes could have carried a different surface signature from the one associated with plants today. The deeper lesson is not the color itself. It is the danger of expecting life to wear the colors of home. Green is not the universal color of biology. It is one solution, shaped by the history of Earth, the light of the sun, the chemistry of chlorophyll, and the long rise of oxygen. Around another star, under another atmosphere, with other pigments and other pressures, living surfaces may return light in unfamiliar ways. A planet around a red dwarf receives a different balance of light from a planet around a sun-like star. Red dwarfs are cooler and redder, and their light is shifted toward longer wavelengths. If life evolves on a world circling such a star, the pigments that gather energy may not match those that work well under Earth's sunday. The atmosphere may filter the incoming light. Clouds or haze may remove some wavelengths and spare others. Water may shape the spectrum before it reaches the surface. Life, if present, would grow inside those limits. This means that the search for surface biosignatures must stay open. A telescope may one day detect a strange reflectance edge, a rise or fall in brightness at certain wavelengths that does not fit cleanly with bare rock, ice, ocean, or cloud. It may look like a pigment. It may look like chemistry. It may have more than one possible explanation. The task is not to declare life from color alone, but to ask whether the color belongs with other evidence. An atmosphere out of balance, a stable climate, liquid water, seasonal change, or gases that should not persist together without renewal. Salt adds another layer. Many purple microbes known on Earth thrive in hypersaline places, where water is present but loaded with dissolved salts. Salt flats, briny lakes, and trapped basins can become colored by microbial life when conditions are right. From a distance, such places are not soft blue seas. They can be red, pink, violet, brown, or white at the edges where crystals gather. A living surface can be harsh, bright, mineral, and still biological. This connects back to Mars and the icy moons in a quiet way. Ancient Mars may have held brines, salty waters that remained liquid under colder or drier conditions than pure water. Europa's ocean is expected to be salty. Enceladus throws salt-rich grains into space. Salt is not merely seasoning in the chemistry of life. It changes freezing points, shapes membranes, stresses cells, and preserves traces. It can make an environment difficult while also keeping water available. The organisms that live in such conditions on Earth are not primitive in the sense of being simple failures. They are highly adapted survivors, tuned to places that would destroy many other cells. Halophilic archaea manage their internal chemistry against the pull of salt outside them. They keep proteins folded, membranes stable, and energy moving. Their existence is a reminder that life does not only expand into comfort, it also learns the rules of difficult places and stays there. If a distant world has a purple signature, it may not be a twin of early Earth. It may be something else entirely. Mineral deposits, photochemical haze, unusual ice, or surface chemistry made by radiation. The same color can have several causes. That is why astrobiology treats beauty with caution. A beautiful signal can still be abiotic. A dull signal can still hide biology. The memory of a possible purple Earth remains useful because it loosens the grip of the present. Earth has not always looked like Earth. Its life has not always shaped the same air or reflected the same light. The planet now known for blue oceans and green continents spent long ages as a microbial world, changing slowly, almost invisibly, while the larger forms of life had not yet arrived. Somewhere else, a world may be in that kind of early chapter. Its life, if it exists, may lie in mats, films, brines, vents, or shallow basins under a strange star. It may never grow a forest. It may never make oxygen in the way Earth did. It may still leave a color behind, slight and patient, written into the light that crosses interstellar space. The color may not be purple. The lesson remains. The word extremophile sounds as if it belongs to the edge of life. In one sense, it does. These organisms live where heat, cold, salt, acid, pressure, dryness, or radiation would kill most familiar forms. Yet they are not strange because they are barely alive. They are strange because they are fully alive in places that seem designed against biology. Their cells still divide. Their enzymes still work. Their membranes still hold one side apart from another. Life continues, but under rules that feel less forgiving. They are quiet teachers because they change the question. Instead of asking only where life would be comfortable, astrobiology asks where life could remain possible. Comfort is a human measure. A microbe has no need for blue sky, soft air, or mild weather. It needs chemistry that can keep moving, a solvent that allows reactions, a way to gather energy, and enough stability for information to be copied through time. Many environments that fail the human test may still pass a microbial one. On Earth, such environments are scattered everywhere. Some are hot springs where mineral water rises from below and paints the ground in bright bands. Some are acidic pools where metals dissolve into colors that look almost unreal. Some are salt flats where water becomes brine and crystals gather around the edges. Some lie beneath desert stones, in thin shaded pockets, where moisture appears only briefly and sunlight is filtered through quartz. Some are buried under ice, locked into cold that slows almost every reaction. Some are deep under the sea, where pressure changes the behavior of proteins and membranes. The Atacama Desert in Chile is one of the clearest examples. It is among the driest non-polar deserts on Earth, with harsh ultraviolet light, salty soils, and long stretches where water is scarce enough to make even microbial life patchy. From orbit, parts of it seem pale, mineral, and nearly empty. On the ground, life is present, but unevenly. It hides where small advantages gather. Beneath rocks, inside salt, in soil layers that catch traces of moisture, around minerals that can protect cells from radiation. That patchiness matters. It shows that habitability is not always a broad region spread smoothly across a landscape. It can exist in small pockets. A world may be mostly hostile and still contain narrow places where life can persist. Mars, if it ever carried life, may have held it in that way near the end. Not everywhere, not openly, but in protected microenvironments where salt, ice, minerals, or rock soften the planet's harsher conditions. Hyperlithic microbes, which live underneath translucent stones in deserts, show how small that shelter can be. A piece of quartz can act like a roof and a window at once. It lets in enough light for photosynthesis, while blocking some of the most damaging radiation and trapping a little moisture beneath it. There is no forest there, no visible green field, only a hidden film of cells under stone. From above, the place may look dead. Up close, the boundary between life and non-life becomes thinner. Other organisms teach different lessons. Halophiles live in salt-heavy environments that draw water out of ordinary cells and disrupt ordinary proteins. To survive, they must manage their internal chemistry with care. Some keep high concentrations of salts inside themselves. Some use special molecules to protect their proteins. Their world is water, but water made difficult. This is useful for thinking about brines on Mars, salty oceans under Europa's ice, and the salt-rich grains that Enceladus throws into space. Psychrophiles, organisms adapted to cold, work at the other end of sensation. Cold slows chemistry, membranes stiffen, enzymes become less flexible. Ice can damage structures or remove liquid water from where cells need it. Yet, some microbes remain active in cold soils, polar ice, sea ice, and subglacial environments. They adjust their membranes, make proteins that function at low temperature, and sometimes use salts or other compounds to keep tiny amounts of liquid water available. Their lesson is not that cold is easy. It is that cold is not always final. Radiation-resistant organisms add another piece. Some microbes can survive damage that would shred the genetic material of many other cells. They do this not by being untouched, but by repairing themselves. Their DNA can break, and their chemistry can put it back together with a skill that seems almost patient. On worlds with thin atmospheres, weak magnetic shielding, or surfaces exposed to charged particles, repair may matter as much as protection. None of this means that Mars, Europa, or Enceladus must contain life. Extremophiles are sometimes misunderstood in that way. Their existence does not prove that every harsh place is inhabited. A place can be habitable for some Earth organisms and still be empty. It may lack the right history, the right chemistry, or the long chain of steps needed for life to begin. Survival and origin are different problems. A cell that can endure an environment today does not prove that the first cell could have arisen there. That distinction is important and calming. Extremophiles widen the map, but they do not erase the unknown. They show that life can adapt far beyond old assumptions, but adaptation requires life to exist first. The search beyond Earth must therefore ask two questions at once. Could life survive there now? Could life have begun there, or arrived there, or remained from an earlier time when conditions were different? The answers may not match. The value of extremophiles lies in the details of their survival. Their proteins reveal how chemistry can be stabilized under stress. Their membranes show how cells keep boundaries in salt, cold, or pressure. Their pigments show how light can be used in unexpected ways. Their metabolism shows how energy can be drawn from minerals, gases, or chemical gradients instead of sunlight. Each adaptation becomes a clue, not a prediction. In laboratories, these organisms are studied under simulated conditions: Martian dryness and radiation, Europa, like cold and salt, vacuum exposure, freezing, thawing, and long dormancy. The goal is not to create a catalogue of alien life by copying Earth microbes onto other worlds. It is to learn what kinds of signatures living systems leave behind when they are stressed. A cell under pressure may change the molecules it produces. A microbe in salt may leave minerals altered in a certain way. A dormant organism may preserve fragile traces long after activity has slowed. Those traces guide instruments. A rover on Mars does not simply look for a living cell moving in the dust. It may search for organic molecules protected under the surface. Minerals formed in water, textures that resemble microbial mats, or chemical patterns that are hard to explain by geology alone. A future plume mission at Enceladus may search for distributions of molecules that look selected rather than random. A probe in Europa's ocean may look for gradients that should have faded unless something keeps renewing them. The teachers remain small: a yeast in a desert rock, an archaeon in a salt lake, a bacterium repairing itself after radiation, a microbe living slowly beneath ice. They do not resemble the imagined aliens of old stories. And that is the point. The first life found beyond Earth, if it is ever found, may be closer to them than to anything with eyes, limbs, or a voice. It may be a cell, or the residue of a cell, or a pattern left by a metabolism too faint to notice without careful instruments. On a quiet night, the thought can settle gently. The universe may not need to produce familiar life in order to produce life at all. It may begin with the small, the hidden, the patient. Earth's extremophiles do not answer whether other worlds are alive. They teach how to ask without assuming that life must prefer the places where humans feel at home. Mars is often imagined as a dead desert because that is how it first appears. Its sky is thin, its surface is cold, dry, and dusted in iron-rich soil that gives the planet its familiar red color. There are no open seas, no rivers moving under clouds, no rain softening the ground. From orbit, much of it looks still, as if time has passed over it and left only stone. But Mars is not simple stillness. It is a planet full of memory. Across its surface are valleys, deltas, lake beds, minerals formed in water, and layered sediments that speak of conditions unlike the Mars seen today. The present planet is dry at the surface, but the older planet carried liquid water in ways that shaped the land. Channels were cut, craters became basins, clay minerals formed, salts were left behind as water vanished. The red desert is not only a desert, it is the remains of environments that have changed. That is why Earth's deserts matter. They do not reproduce Mars perfectly. No place on Earth does. Earth has a thick atmosphere, a strong biosphere, active weather, oceans, and oxygen-rich air. Mars has none of those in the same way. Yet, some deserts offer narrow pieces of the Martian problem: dryness, salt, ultraviolet radiation, oxidizing soils, cold nights, and long periods when liquid water is almost absent. A desert can become a partial mirror, not of the whole planet, but of the pressures life might face there. The Atacama Desert is one of the clearest mirrors. In its driest regions, rain can be absent for long stretches, and the ground can seem almost sterile. The sunlight is harsh. Salts gather in the soil. Organic traces are faint and difficult to detect. Life, where it exists, does not spread evenly across the landscape. It hides in patches, tied to small differences that might be easy to miss. A stone that offers shade, a layer that holds a little moisture, a salt deposit that traps water from the air, a depth where radiation is weaker. Patchiness is a quiet but important lesson. A mission searching for life on Mars cannot assume that one scoop of soil speaks for a whole landscape. A barren patch may lie beside a protected pocket. A dry surface may cover a more interesting layer below. Even on Earth, where life is abundant overall, the most Mars-like places can make biology difficult to find. The absence of an easy signal does not close the question. Under translucent stones in desert regions, microbes sometimes live in thin, sheltered films. The stone lets some light through while softening the damage from direct exposure. Beneath the surface, other communities may survive, where the soil holds traces of moisture or where salts change the behavior of water. These are not lush environments. They are small negotiations with hardship. Life persists by using margins. Mars, if it ever carried life, may have required the same modesty. It may not have been a living planet in the way Earth is now, covered with a biosphere that announces itself through air, ocean, and green land. It may have held life only in limited places, during limited windows of time, perhaps near water, heat, minerals, or buried ice. A cell on such a world would not need Mars to be kind everywhere. It would need one place to remain workable long enough. Some of the most interesting places may have been hydrothermal. On Earth, hot springs and steam vents can preserve traces of microbial life in silica and other mineral deposits. Water rises, cools, evaporates, leaves minerals behind, and sometimes traps delicate textures or chemical patterns. Such places combine energy, water, rock, and surfaces where chemistry can concentrate. They are not only habitats, they can become archives. The Spirit rover found one of the most suggestive Martian examples in Gusev crater. Its damaged wheel, dragging through the soil near a region called Home Plate, uncovered bright material rich in silica. The discovery was unexpected, almost accidental. Silica like that can form in environments involving water, including hot springs or steam vents. On Earth, similar settings can be friendly to microbial life and good at preserving its traces. There is a softness in that accident. A broken wheel, a strip of disturbed soil, and suddenly the planet revealed something the mission had not planned in that exact way. Mars did not become alive because of that discovery. It did become more textured. It showed that even a place now cold and dry once held chemical environments where water and heat may have met. Gusev crater is not the whole story. Mars has many kinds of watery memory. Some regions contain clays, which form when rock and water interact over time. Some contain sulfates, often linked to acidic waters and evaporation. Some contain carbonates, minerals that can form in less acidic conditions, and may preserve clues about ancient atmosphere and water chemistry. Each mineral is a small testimony, not only that water existed, but that the character of the water changed from place to place. That variety matters for life. Water alone is not enough. The chemistry of the water matters. Acidic water is different from neutral water. Fresh water is different from brine. A short flood is different from a stable lake. A hot spring is different from a cold underground seep. Mars may have offered many environments, but not all of them would have been equally useful to biology. Brines are especially important because salty water can remain liquid under conditions where pure water would freeze or evaporate. Ancient Mars may have held briny pockets as its climate changed and surface water became harder to sustain. Salt can help keep water available, but it also stresses cells. Too much salt can pull water out of life. Again, Mars becomes a planet of margins, where something helpful and something harmful may be the same thing at different strengths. The Atacama helps hold that contradiction. Some of its salty places preserve microbial life. Others are so dry and chemically harsh that life becomes sparse or difficult to detect. Instruments tested there must learn how to drill, sample, avoid contamination, and recognize faint traces without being fooled by minerals or destroyed organic material. The work is slow because the target is not obvious. A rover may need to search beneath the surface, where radiation has not erased as much, and where the record may be less exposed. This is why Mars is not only a destination, it is a lesson in how life can disappear from sight. If the planet once had life, that life may now be gone, dormant, buried, or preserved only as chemistry in stone. The search may not be for living cells moving in the dust. It may be for carbon patterns, mineral textures, isotopic ratios, or organic molecules protected in ancient deposits. It may be for the shadow of a biosphere rather than the biosphere itself. The red planet teaches caution. It once had water, but water did not make its surface remain like Earth. It may have had habitable places, but habitability does not guarantee biology. It holds minerals that preserve memory, but memory can be blurred by time, radiation, and dust. Mars is close enough to study with rovers and orbiters, yet distant enough to keep its deepest answer just beyond reach. From Earth's deserts, the lesson returns quietly. Life can be patchy, traces can be fragile, a world can look empty from above and still hold protected places below. Mars may be a desert now, but it is not an empty idea. It is an archive of lost water, altered rock, ancient heat, and the long uncertainty of whether chemistry there ever crossed into life. The phrase Earth 2 is gentle and dangerous at the same time. It suggests a second home, waiting somewhere in the dark, a planet with blue water, mild air, open land, and a gravity that feels like the body already knows it. In the language of headlines, a world can become Earth-like very quickly. In the language of science, the same world usually becomes more complicated the longer it is studied. Thousands of planets have now been confirmed around other stars. Some are larger than Jupiter, some are smaller than Neptune. Some skim so close to their stars that their years last only a few days. Some are rocky, some gaseous, some swollen by heat, some locked in cold orbits where sunlight is faint. The number itself creates a quiet optimism. If planets are common, and if the galaxy is old, then somewhere among them there may be worlds with oceans, atmospheres, and surfaces stable enough for life. That hope is reasonable. The mistake begins when a few measurements are asked to carry too much. Most exoplanets are not seen as disks with weather, oceans, and continents. They are found through indirect signs: a star dimming when a planet crosses in front of it, a star wobbling under the pull of an unseen companion, a change in light that repeats with mathematical patience. From those signals, astronomers may learn a planet's size, orbit, sometimes mass, sometimes density, and sometimes a little about its atmosphere. These are powerful clues, but they are not a lived world. The habitable zone is one of the most useful and most misunderstood clues. It describes the range of distances from a star where liquid water could exist on a planet's surface if the planet has the right atmosphere. The final phrase matters. Distance alone does not make a climate. Venus sits near the inner edge of the Sun's habitable region, yet its atmosphere traps heat so strongly that its surface destroys ordinary spacecraft in a short time. Mars sits farther out, with evidence of ancient water, yet its present surface is cold and dry beneath thin air. A planet can be in the right place and still be wrong in almost every other way. The star itself is the next question. Many planets that attract interest orbit red dwarfs, the small, cool stars that make up much of the galaxy's stellar population. Red dwarfs are long-lived and their long lives seem at first like a gift. A stable star that burns for trillions of years could give biology time beyond any timescale Earth has known. Yet their habitable zones lie close in, because the stars are dim. A planet must orbit near the star to receive enough warmth. Nearness brings problems. Many red dwarfs are active, especially in youth. They can release flares and streams of high-energy radiation that strike nearby planets with force. If a planet has no strong protection, such radiation can erode its atmosphere, change its chemistry, and expose the surface to conditions unfriendly to life as known on Earth. Proxima Centauri b, the nearest known exoplanet to the solar system, is often mentioned because of its location and possible rocky nature. Its closeness makes it reachable to imagination, not yet to travel, and it also places it inside the difficult weather of its star. Close orbits can also bring tidal locking. Over time, gravity may slow a planet's rotation until the same side always faces the star. One hemisphere receives permanent day, the other remains in permanent night. The line between them, the terminator, may be a band of long twilight. The day side could be too hot. The night side could freeze. Winds might move heat around the planet, and a thick enough atmosphere could soften the contrast. But the climate would not resemble Earth's daily rhythm. No sunrise would move across the ground. Tidal locking does not automatically mean a world is dead. This is where older assumptions have softened. Climate models suggest that some locked planets, under the right conditions, could move heat from day to night and keep regions temperate. Clouds might form over the hot side and reflect starlight. Atmospheres and oceans, if they exist, might carry warmth into darkness. A locked planet may be strange without being impossible. The point is not rejection. The point is care. Gravity asks another kind of care. A rocky planet larger than Earth may hold an atmosphere well, and it may have geology that stays active for long periods. Yet a larger mass can mean stronger surface gravity. For microbes, that may matter little. For human bodies, it matters a great deal. Muscles, bones, circulation, breathing, pregnancy, childhood, injury, and aging all evolved under Earth's pull. A planet with twice Earth's surface gravity would not simply feel heavy for a moment. It would make every standing hour more expensive. Sleep would press harder. Walking would become labor. Lower gravity seems kinder at first, but the human body also loses what it is not asked to use. Astronauts in orbit show how bones, muscles, fluids, eyes, and the cardiovascular system respond when weight is reduced for long periods. Mars and the Moon are not weightless, yet they are far below Earth's gravity. Long-term settlement there would not be only an engineering problem, it would be a biological experiment carried by everybody that tried to remain. Atmosphere completes the uncertainty. A planet may be rocky and well-placed, yet have no air. It may have air too thin to warm the surface, or too thick to permit anything like a human climate. It may have gases that poison Earth life, clouds that hide the surface, pressures that crush, or winds shaped by a rotation and orbit unlike anything familiar. An atmosphere can protect, warm, suffocate, strip away, or transform a world. This is why the idea of Earth too must stay slow. There may indeed be planets that are close to Earth in size, orbit, and temperature. Some may be far better homes for microbes than for humans. Some may be habitable in a scientific sense while being unlivable for the human body. Some may carry oceans under red skies, locked beneath one steady sun, with chemistry that never once needed to become comfortable. The search remains beautiful because of that. Not every promising world must become a future address. A planet can matter without being a home. It can teach how atmospheres survive, how stars shape climates, how water behaves under other skies, and how narrow or wide the conditions for life may be. Earth is not only a template, it is also a warning against expecting the universe to repeat itself too neatly. Somewhere in the galaxy, there may be a world that comes close enough to deserve the old dream. For now, every candidate remains partly hidden inside light, models, and careful doubt. The second Earth has not been found. What has been found is stranger. A galaxy full of planets, each one reminding science that habitability is not a label, but a long conversation between star, rock, air, water, time, and life. A telescope does not travel to the planets it studies. It waits. It gathers light that has crossed emptiness without knowing where it is going. It holds that light for a moment inside mirrors, detectors, filters, and cold instruments, then turns it into measurements delicate enough to suggest the presence of air around a world no human eye can see as a disk. This is one of the quietest forms of exploration. No wheel touches dust. No lander settles under alien gravity. No probe passes through a plume of ice. A planet hundreds of light years away moves across the face of its star, and during that small alignment, a thin ring of atmosphere alters the starlight passing through it. The planet becomes known by the colors it removes. JWST has made that kind of reading more powerful. It was not built only for exoplanets, but its large mirror, cold instruments, and infrared vision have opened a clearer way to study distant atmospheres around WASP 39b, a hot gas giant far from being habitable. JWST detected carbon dioxide in the planet's atmosphere with clarity that older observations could not reach. That planet is not a second Earth. It is too hot, too large, too close to its star. Yet the detection mattered because it showed how sharply a distant atmosphere could be read. A world does not need to be habitable to teach the method. Hot giant planets are easier targets because their atmospheres are large and swollen. Their signals are stronger. Starlight passes through more gas before reaching the telescope. The lessons learned from them become practice for smaller, colder, harder worlds. The instrument learns how clouds hide features, how molecules overlap, how a star's own behavior can confuse a spectrum, and how repeated observations can turn faint patterns into something steadier. In this work, air becomes a record. Carbon dioxide can speak of formation, temperature, and chemistry. Water vapor can suggest heat, circulation, and atmospheric structure. Methane can appear from biology in some settings and from geology or chemistry in others. Oxygen can be powerful, but only when its context is understood. No gas is innocent. No gas is final by itself. The star must be studied alongside the planet. A restless star can flare, spot, brighten, dim, and leave marks in the data that resemble planetary features. A calm star makes the reading easier, though never easy. The size of the planet, the height of its atmosphere, the presence of clouds, the timing of its orbit, the color of the star, and the noise inside the instrument all become part of the same slow equation. The atmosphere is not simply seen. It is separated from everything that tries to imitate it. There is another path besides waiting for a planet to pass in front of its star. Direct imaging tries to see the planet's own light beside the overwhelming glare of the star. The difficulty is almost unfair. A star can be billions of times brighter than the small world beside it. The planet is close to the star in the sky, not because it is close in space, but because distance compresses everything. Seeing it is like trying to notice a firefly near a searchlight from far across a dark field. Coronagraphs help by blocking the star's glare. They use masks, mirrors, detectors, and careful optics to suppress the light of the star so that the much fainter planet can emerge. The Roman Space Telescope is meant to carry a coronagraph as a technology demonstration. a step toward seeing planets more directly from space. Its first targets will not be small Earth twins with oceans and clouds. The task is to prove control, contrast, stability, and patience. The path toward faint rocky worlds begins with larger and brighter ones. Beyond Roman lies the idea of the Habitable Worlds Observatory. Its name carries the long intention openly. It is being planned as a future mission designed to directly image potentially habitable planets around other stars and study their atmospheres for possible biosignatures. Such a mission would not simply count planets. It would ask whether nearby stars host worlds where water, air, chemistry, and perhaps biology have shaped a detectable signal. The goal is not a photograph like a landscape. Even a directly imaged rocky exoplanet would likely appear as a point, maybe a pale pixel separated from its star. But that pixel could be split into colors. The colors could reveal gases. Repeated observations could show rotation, clouds, seasons, or surface changes. A small point of light could slowly become a world with weather, atmosphere, and unanswered possibilities. That is the strange intimacy of astronomy. The object remains unreachable, but knowledge grows close. A telescope can never feel wind on the surface of a distant planet. Yet it may learn that the air contains water vapor. It cannot see an ocean wave, yet it may detect the glint or color of a surface. It cannot watch a microbe divide, yet it may find gases that refuse to settle into chemical peace. The search for life through telescopes will depend on combinations: oxygen with methane, carbon dioxide with water vapor, atmospheric pressure, hinted by broad absorption, clouds inferred from muted features, a planet's orbit placing it in a temperature range where liquid water could be possible, a star old enough and calm enough to allow time. None of these alone is enough. Together, they may begin to lean. Even then, doubt will remain. A lifeless planet can fool an eager observer. Ultraviolet light can split water and leave oxygen behind. Volcanism can release gases that look active. Photochemistry can build hazes. Impacts can change atmospheres. A biosignature must survive not only detection, but explanation. The better question may not be whether a gas could come from life, but whether all known non-living routes can be made less convincing. This is slow work by design. It may take many transits to build a spectrum. It may take years to watch a planet through its orbit. It may take a future telescope, then another future telescope, before a rocky world around a nearby star becomes readable in the way hot giants are readable now. The universe allows no hurry here. The light arrives when it arrives, and the instruments must be ready. There is comfort in that patience. The search does not depend on one sudden revelation. It grows through practice. First, a hot giant's carbon dioxide, then smaller planets, then colder planets, then better suppression of starlight, then spectra of worlds that once would have been lost entirely inside glare. Each step teaches the next one where to be careful. Somewhere, a planet may be crossing its star tonight. Its atmosphere may be thin, cloudy, dry, wet, dead, active, or alive. From Earth, it is only a slight dimming in a distant point of light. The telescope waits through that dimming and keeps the colors that pass through the planet's air. In those colors, there may one day be a pattern that does not shout, does not prove itself at once, and does not look like a face in the dark. It may be only distant air, refusing to make chemical sense without life. Before life has a name, it is chemistry in motion. There is no cell yet, no organism, no inheritance in the full sense, no thin boundary that clearly says inside and outside. There is only a young planet with oceans, rock, heat, lightning, impacts, minerals, gases, and time. Molecules form, break, drift, settle, and meet again. Most of those meetings lead nowhere. A few may linger. The early Earth is not gentle. Its surface is still cooling from violence. Volcanoes release gases into a different sky. Meteorites and comets bring material from beyond the planet. The moon hangs closer than it does now. Oceans gather as the crust changes beneath them. There is no grass, no oxygen-rich air, no animal sound, no shore as it would be known today. Only water, stone, heat, and restless chemistry. Life, as it exists now, seems almost impossible when viewed from that distance. A modern cell is not a simple droplet. It is a boundary, a library, a power system, and a repair shop, all operating at once. It stores information, turns energy into work, builds proteins, and controls what enters and leaves. To ask how such a thing began is to ask how small chemical habits became linked until they crossed a threshold. The first part of that threshold may have been a wall. Fatty acids are simple compared with the complex lipids in modern cell membranes, but they have a useful shape. One end is drawn toward water, the other avoids it. When enough of these molecules gather in water, they can arrange themselves into hollow spheres, with water-loving heads facing outward and inward, and water-avoiding tails tucked away from the surrounding liquid. A tiny compartment appears without a hand designing it. That compartment is not alive. It is only a bubble-like boundary. Still, a boundary changes everything. Inside can become different from outside. Molecules can be held near one another instead of drifting away into the wider ocean. Reactions can become more likely because the ingredients remain close. A fragile little chamber can grow by taking in more fatty acids. Under some conditions it can divide, not with purpose, just through the ordinary physics of surfaces, tension, and motion. A protocell is a useful name for such a half-step. It is not yet a cell in the modern sense. It has no complete genetic system, no polished metabolism, no long chain of ancestors behind it. It is a container where chemistry can be gathered, protected, and tested. Many protocells would fail. Their membranes would leak, collapse, divide unevenly, or carry nothing useful. Failure would not matter if the planet made them again and again. Information is the next quiet problem. Modern life uses DNA to store genetic instructions, RNA to help read and carry those instructions, and proteins to perform much of the cell's work. This arrangement is sometimes described as a central flow of information from DNA to RNA to protein. It is elegant now, but too complex to be the first step. The early system likely had to be rougher. RNA draws attention because it can carry information and, in some forms, help catalyze reactions. It stands between storage and action. That does not mean early Earth simply produced perfect RNA strands and life followed. The chemistry is difficult. Nucleotides, the building blocks of RNA, must form, survive, link together, and remain useful in an environment full of competing reactions. The RNA world is not a solved story. It is a doorway into the problem. Even an imperfect strand could matter if it changed the chemistry around it. A short chain might help one reaction happen faster. Another might bind certain molecules. Another might fall apart. In a population of compartments, small differences could begin to matter. A protocell carrying chemistry that helped it grow, remain stable, or divide more often would become more common than one without those advantages. Selection does not need eyes. It only needs variation and consequences. Proteins, or their simpler ancestors, bring another layer. Amino acids can form under prebiotic conditions and have been found in meteorites, which means some of life's ingredients are not confined to Earth's surface. Amino acids can link into short chains called peptides. Some peptides can stabilize membranes, some can help reactions, some can bind metals. Long before modern enzymes, smaller molecular helpers may have made certain pathways easier than others. Metabolism may also have begun before life was fully alive. In modern cells, metabolism is a network of reactions that moves energy and matter through controlled steps. On the early Earth, some reaction networks may have been self-reinforcing. A product of one reaction could help produce more of itself, or help maintain the pathway that made it. These are autocatalytic patterns, chemistry that begins to feed its own continuation. Such patterns are not organisms. They do not have hunger or desire, yet they create something life later depends on: persistence. A pathway that reinforces itself can become more common in the right environment. If enclosed in a compartment, it may help that compartment grow or divide. If linked to molecules that carry information, it may become part of a cycle where chemistry, boundary, and inheritance begin to pull on one another. No single molecule is likely to explain the whole beginning. A membrane without information is temporary. Information without a compartment can diffuse into the world. Metabolism without inheritance may keep reacting without evolving. The origin of life may have required these pieces to approach one another gradually, not as finished systems, but as rough partnerships. A boundary holds chemistry. Chemistry supports the boundary. Information preserves useful accidents. The setting matters as much as the molecules. Drying and wetting cycles near hot springs could concentrate ingredients, link molecules together, then return them to water. Mineral surfaces could hold molecules in place and shape reactions. Hydrothermal vents could provide steady chemical gradients, where warm, mineral-rich fluids meet cooler ocean water. Pores in rocks could act like natural compartments before membranes became reliable. Different origin stories favor different landscapes, and none has closed the question. That uncertainty is honest. The first life left no witness. Rocks from that time have been altered, buried, melted, and broken by the restless planet that later life would inhabit. Science can reconstruct pathways, test reactions, build protocells, and compare ancient patterns. It cannot yet point to one pool, one vent, one moment, and say that life began there. What it can say is still enough to change the feeling of the universe. The ingredients of life are not magical objects placed separately from ordinary chemistry. Fatty acids can form boundaries. Amino acids can make useful chains. Nucleotides can carry patterns. Chemical networks can reinforce themselves. Energy gradients can drive reactions away from stillness. On a young, wet planet, these pieces do not have to know what they are becoming. They only have to keep happening in the right places for long enough. The first darkness that mattered to life may not have been cold. It may have been warm, mineral, and hidden underwater. Not the open darkness between stars, and not the empty darkness of a dead world, but a darkness with movement inside it. Water passing through rock, heat rising through cracks, hydrogen forming where minerals changed, carbon dioxide dissolved in ancient seas, gradients held in stone. On the early Earth, sunlight was not the only source of useful energy. The young planet had an interior still releasing heat, a crust still changing, and oceans lying over a world that had not settled into its later forms. Where seawater entered fractured rock and returned altered, chemistry could be pushed away from stillness. In such places, the planet did not need a bright surface to become active. It only needed differences strong enough for molecules to follow. Hydrothermal vents offer one possible setting for that beginning. They are not simple chimneys of hot water. They are meeting places. Warm alkaline fluids from the interior can meet cooler, more acidic ocean water. Minerals can form thin walls and tiny pores. Across those boundaries, chemical differences can persist. One side is not like the other. For living cells today, that kind of difference is essential. Cells keep gradients across membranes, then use those gradients to make energy available for work. This resemblance does not prove that life began at vents. It gives the idea weight. A vent system already has compartments, surfaces, flows, and energy differences before life arrives. The rock itself can play part of the role that a cell membrane later plays, holding one chemistry close to another while keeping them separated enough for work to be done. In the small pores of mineral structures, molecules may gather instead of dispersing into the wider sea. Reactions may repeat. Products may remain near the places that made them. The beginning, if it happened there, would not look alive at first. No cell would swim into view. No organism would appear complete. The scene would be chemical and slow. Carbon compounds forming, metal minerals helping reactions, hydrogen offering electrons, carbon dioxide accepting them, small molecules becoming linked into larger ones, and some pathways repeating more easily than others. Most of it would fail. Some of it might persist. Persistence is the quiet word underneath the origin of life. A molecule that lasts a little longer matters. A reaction that feeds back on itself matters. A boundary that holds ingredients together matters. A pathway that can use the energy of its surroundings matters. None of these alone is life, but together they begin to resemble the habits life later keeps. Luca, the last universal common ancestor, was not the first life. It was already advanced compared with whatever came before it. Every organism alive today, from trees to whales to microbes in salt lakes and cells inside the human body, descends from a lineage that passes through that ancient common ancestor. Luca had genes, metabolism, and an inheritance system. It was not a loose chemical cloud. It was a living organism, or at least part of a living population, already on the far side of the threshold. Yet clues from modern biology suggest that Luca may have belonged to a hot, oxygen-free world, rich in hydrogen and carbon dioxide. Some reconstructions point toward a metabolism that used hydrogen as an energy source and fixed carbon dioxide into organic molecules. That picture fits naturally with hydrothermal settings, especially those where water-rock reactions produce hydrogen. It also places the earliest shared ancestor of life, close to the same kinds of chemistry that make ocean worlds interesting now. There is a gentle circle in that. Earth's deep vents help explain why scientists look at Europa and Enceladus. Europa may have a dark ocean-touching rock under ice. Enceladus sends grains of its ocean into space, carrying signs of salts, organics, hydrogen, and other ingredients. If water-rock reactions can make chemical energy on Earth, then similar reactions elsewhere may create habitats that do not need sunlight. The same idea moves from the ancient seafloor to the outer solar system. That does not mean life easily begins wherever vents exist. Origin is not the same as survival. A hydrothermal system may feed living cells once they are present and still fail to create the first ones. Conditions may be too hot, too unstable, too dilute, too chemically limited, or too short-lived. Other origin settings remain possible. Warm ponds that dry and refill, volcanic pools, mineral surfaces near the surface, impact, shaped environments, ice, or combinations of several places across time. The first life may not belong to one scene alone. Still, the vent image holds because it joins so many necessary pieces: water, rock, heat, chemical imbalance, natural compartments, mineral catalysts, a flow of matter from one state to another. In a universe where light is often weak, blocked, or absent, this matters. It says that life's earliest doorway may not require a sky. The early Earth did eventually become a planet of sunlight. Photosynthesis changed the atmosphere. Oxygen accumulated. Complex cells emerged. Multicellular life followed much later. Forests, animals, and human eyes are late arrivals. The first story was smaller and darker. It belonged to cells without oxygen, to chemistry that used what the planet offered before the air became breathable, before blue skies meant safety, before life had remade the surface enough to seem inevitable. This makes the search beyond Earth less lonely. It shifts attention from planets that look like home to environments that work like beginnings. A buried ocean may matter. A warm rock-water interface may matter. A plume escaping through cracks may matter. A salty brine protected beneath the surface may matter. The question becomes less about finding another Earth as it is now, and more about finding places where chemistry has not gone still. The first warm darkness is gone from Earth in its original form. The planet has changed too much, and life itself has altered the conditions under which it began. Oxygen fills the air. Biology occupies the oceans, soils, rocks, and clouds. If new life tried to start here now, existing life would likely consume its ingredients before it ever crossed the threshold. The beginning has been buried by everything that followed. But elsewhere, beginnings may still be possible. Under ice, inside rock, beneath old seas, around vents no eye has seen. Chemistry may be working through its long chances. It may never become life. It may stop at complexity and go no further. Or, in some hidden place, a boundary may hold, an energy flow may persist, and molecules may begin to remember their own pattern. Life may not begin in brightness. It may begin where the world is sealed, warm, and dark, with water moving through stone. The journey does not need to end with an answer. It can end the way deep water ends in darkness, without a hard border, without a final wall, only with the sense that something vast continues beyond the reach of the light. Far out in the solar system, the icy moons keep turning. Europa carries its pale shell around Jupiter. Enceladus releases fine grains of its hidden ocean into the cold space near Saturn. Mars holds its dry valleys and mineral memories under a thin sky. Around other stars, planets cross slowly in front of their suns, changing the light by almost nothing, leaving only the faintest traces of distant air. Earth turns too. Above the ocean, clouds move across the night side of the planet. Waves lift and settle. Far below them, trenches remain black and still. Somewhere near a vent, warm water rises through stone, and small forms of life continue their quiet chemistry without needing sunrise. The same planet that looks blue from space keeps these hidden rooms beneath its surface, old and patient, carrying lessons that reach outward toward moons, planets, and seas no one has entered. Let the images grow softer now. The ice can fade, the instruments can fall silent, the distant stars can become only small points in the dark, not questions to solve, only lights remaining where they are. There is no need to follow every orbit, every molecule, every name. The story has already moved through water, rock, salt, darkness, and time. And now it can drift without effort. The room is here again. The body is here. The breath returns to its ordinary rhythm. Somewhere beyond the window, the sky continues without asking anything. Somewhere far away, hidden oceans may still be moving under ice. For now, it is enough to rest.